This week is all about atmospheric pressure. You may not have realized that air has weight, and meteorologists use that to forecast whether there's going to be showers around or sunny skies. Most high pressure systems in the atmosphere tend to lead to nice weather, sunny weather. Many low pressure systems bring clouds, precipitation of some form. So here is a surface weather map, and you can see nice high pressure up over Canada. And there's a lot of high pressure across the eastern two-thirds of the U.S. here. Almost all connected. And this is the area that's getting a lot of heat right now and all nice warm air there. So notice how the pressure gradient, the change in pressure, is not a lot between any of these things. A lot more up here in Canada, but not much across most of the United States. So we can look at that, actually see how pressure changes from day to day. So we'll look here at Mansfield, Ohio. And here are the dots. This actually is June 30th. And all these is dates and times. So every one of these is an hour observation. So we can see here the pressure started out at 1,016.4 millibars, dropped off down here by evening. And we'll go back here a second and see if we can change that back to the graph we were on. And here's the 1,000, back up again, there's 1,015. These are not huge pressure differences. 1,018. The pressure changed from 7:52 p.m. to 10 a.m. So a course of over 12 hours when the pressure rose a whopping 3 millibars. Not a lot of change in the horizontal, and even less than that over the rest of this graph. So you can see the pressure doesn't change a lot. I mean, yes, there's mainly high pressure over the area, but even when there's low pressure approaching, pressure changes are relatively minimal when you compare them in the vertical. This is 500 millibar chart. So everything here is 500 millibars. So that means, say, the pressure at the surface was 1,000. The pressure aloft is 500. So here is 5,920 millibar. Contours, excuse me, 5,920 meters. Here's a 5,940 meters. And that is what is on that line right here. So if you multiply that by 3, roughly 18,000 feet, ballparking. So a little over 3 miles up in the atmosphere. And yet the difference in pressure is 500 millibars. The difference in pressure in the horizontal, very minimal compared to that 3 millibars over a course of a day. If you looked at the surface weather map, you can see you got to go large distances to get that kind of change. So we want to understand why that is. What has caused pressure to change like that? Why does pressure change? Look here, a lot of hot air right here, and this is the highest area pressure changes, much higher than where the air is colder. Well, let's look at some of this now and see why some of these things are occurring. We'll start back here at the beginning again. And what is the significance of horizontal and vertical variations in air pressure and what they are? So let's define air pressure. Force is mass, in other words, how many molecules, how much of matter is in some space times how much of acceleration it has. So if you took a car, it has so much mass and it's accelerated then by your foot using the gas pedal. The two together are a force, the force that moves you and that car somewhere. Same thing happens to the atmosphere. All these air molecules hit at random motion. The more they collide with other molecules, and all the more pressure is built up. And the cumulative force of all these collisions is the total air pressure. And interestingly, our friend Dalton again has said that the total pressure exerted by the mixture of all gases equals the sum of the pressures by each individual gas. So in other words, we know the atmosphere is made up of nitrogen, carbon dioxide, oxygen, water vapor. Each one of those has a pressure associated with it. Their pressures combine to give the actual atmospheric pressure. So air pressure will depend on the mass of the molecules, how heavy they are, and how much energy they have. Average sea level pressure, about 1 kilogram per every cubic centimeter, or 14.7 pounds per every square inch. So on your body, your weight right now, you're weighing down by 14.7 pounds for every square inch of your body. You think, man, that's a lot of weight. Yet you're not collapsing because your body has air in it and pushes back against that. Some of the ways we measure pressure, the very first one was used by a mercury barometer. We no longer use mercury because we've discovered that it's not a good chemical to work with. But the same thing applies in the sense of, oh, we have a tube with a vacuum in it. We put it in some form of a chemical that is nice and heavy. That vacuum, then the air pushes down on that liquid, pushes it up the tube, and you get an air pressure. Aneroid barometers are another method we use. And here is a way we record that pressure in barographs. You saw one of those earlier. So the usual measure that we'll look for in the United States is we use millibars on all of our surface weather maps. You've seen a lot of that, and you're going to see a lot more as we go along in this course. That can be relatively easily converted to the worldwide standard of pascals. 1 hectopascal is basically the same as 1 millibar. Now, bars and inches of mercury are very different, and most people in the United States are still used to using inches of mercury. Why is that? Because most home barometers measure that way. So the greatest pressure, because we know air accumulates and there's less and less molecules, so there's less mass the further up you get in the atmosphere. The heaviest air pressure is always going to be near the surface. Not at the top of the mountains, but down at the bottom in the base of the mountains. And by the time you reached 11 miles up, only 10% of the air pressure compared to the surface is there. All right. An interesting thing about air pressure is that it is compressible. Air is compressible. What that means is if I have a volume of air, I can push it together or pull it apart. I cannot do that with water. If you try to push water together, it's going to squirt out. However, on a volume of air, I can push it together, and I can therefore push the molecules closer together, increase the mass, increase the air pressure. So, interestingly, with that, since air pressure is the accumulation of the weight above you, all the molecules above you, because they're being pushed down by gravity pulls air down, we know there are more molecules down near the surface and less the higher up you go. That is why pressure weighs more and drops much quicker in the lower atmosphere compared to the higher atmosphere, where by then you've thinned out the atmosphere as much. Here's what you've seen on all these surface weather maps. Big high pressure here, in this case, over New England, pushing down along the East Coast. Low pressure in the central part of the country. You'd expect nice weather here, bad weather over here. Notice a lot of distances, 1,000 millibars here, 1028 millibars. That's 28 millibars in what? A distance from Iowa to New York City or Boston, several thousand miles. That is not a big change in pressure in the vertical like we have. Horizontal pressures change, but they don't change as fast. And here you can see the variations over the course of the day or two. So, rising air temperature, we know, increases average kinetic molecular activity. We learned that in the last chapter. So, if I put a bunch of molecules together and the atmosphere is not a closed container, I heat them up. What they're going to do is hit the other molecules around them and spread them out. So we wind up with less mass in a given area. Less mass means we have less pressure. So air pressure drops then in colder air much quicker. Cold air is denser, has less kinetic energy, the molecules are closer together. So if you look at in the vertical, cold air will cause the pressure to drop fairly quickly, where in warm air it'll drop slower. So in a warm air mass next to a cold air mass, you're actually increasing the pressure gradient as you go up in the atmosphere. One side's dropping faster, one side's dropping slower. Cold air masses are the densest. They generally produce higher pressures. However, I just showed you a warm air mass that was producing fairly high pressure over the eastern part of the U.S. right now. So it's not a given. But the coldest air masses tend to have the highest pressures on Earth. All right, with this now, the atmosphere is a fluid. So what I do at the top or the bottom or anywhere in vertical along a column of air is going to influence other aspects of that column of air. So if at the bottom of the air column, right by the surface, I pull the air apart for whatever reason, we'll call that divergence. We're pulling the air apart. That means air is going to come down to take its place. It's going to come from the top. With that coming from the top, we're going to tend to cause air converging at the top. So you see how if I have one part divergent, one part's converging. If I flip that and have the divergence aloft, then I'm going to have converging air at the bottom and air tending to rise up. And this can be caused by a number of changes. There could be warm heating of the air. It could be air moving into the coastline, sea breezes, a front. We use isobars, which are lines of equal pressure, to look at highs and lows at the surface. So now we're going to talk about, if I know the pressure and temperature, I can determine the density. The ideal gas law has pressure, temperature, and density as part of each equation. If I know 2 out of the 3, I can always determine the third. All right, we know that air can expand because we've not trapped the air in the atmosphere as such. It can expand or contract. When air expands, its temperature of the air cools. Think about it when you're letting air out of a tire. The air coming out of that tire gets colder and colder. When the air is pushed into a tire with a pump, the air is getting warmer, it's getting compressed. So that all stems from the first law of thermodynamics. It said heat energy gained by an air parcel either increases the parcel's internal energy or is used to do work on the parcel. So if a transfer of heat raises the parcel's air temperature, outside forces are pushing the air together. The air temperature rises. If, however, the parcel is expanding, it's using energy to expand, the parcel lowers. So in the atmosphere itself then, as I go up with an air parcel, as it's rising, it's pushing apart, it's causing the air to expand. which is causing the temperature to cool. That's why in the troposphere, temperatures cool with height. So right here you can see that. And because we can calculate that, we can say if the air is dry, notice I said dry, I'm not dealing with latent heat here, I'm dealing with plain dry air. Temperature will cool at a rate of 9.8 degrees Celsius per 1,000 meters. Works out to about 5.5 degrees Fahrenheit for 1,000 feet. So if I am climbing a mountain upwards, the higher I go, temperatures are going to get cooler. And if it's a dry day, they're probably going to get cooler at about this rate. All right, moisture messes everything up. We learned last week that temperature changes from latent heating. So if I have air that's becoming saturated, it is releasing heat into the atmosphere. That means the temperature can't cool as fast as it would if it was dry. So the moist adiabatic lapse rate is significantly less than the dry adiabatic lapse rate. So we've just now talked a whole bunch about pressure here. So I hope you let me know if you have any questions about this.